So unfortunately, sometime during the first hour, the battery died of the microphone. So let's see if we have audio on the recording. Okay, so what I wanted to say here is, so we have this thing is bounded, it's continuous, it's bounded in and this all in a compact interval. So we can make the interval go from 0 to something that's not infinity, and there we can say that it's bounded from below by C1. And now, I wrote that here. How can we use that? Well then, this here, for all m over n, is also bounded from below by C1, and hence this height of zeta over height of m over n is bounded by this. Now we can just, since we, in this lemma, since we want to work with logarithmic height, we also have to take the logarithm and get that and this is what we wanted to show. Yeah. Is it? Do we have a minus wrong here? So now this is this. No. So this is a plus here. Now it makes sense. Okay, this is what we wanted to show. Good. Now this would have been a good time for a break, but okay. So we proved lemma 3 prime, which was just the finishing part of lemma 3, so we also have lemma 3 proven. And all we need to do is lemma 4. What was lemma 4? Lemma 4 was the hardest part. Lemma 4 is this. Lemma 4 says that the rational points modulo the rational points that are twice the points, twice some point. This is a finite set, or finite group even. So we aren't going to prove lemma 4, but lemma 4 is, in the book they prove it by introducing a nice function on some nice sets or groups that have something to do with the elliptic curve or other elliptic curves. And since we use this thing later to do some other things with ranks of elliptic curves, I want to introduce that function, some properties, but I will not prove all of them. I think I will not prove any of them. But we will keep on using that later. So we won't prove lemma 4. But talk about strategies in the proof. Yeah, I think the chapter in the book is called A Useful Homomorphism, and that's exactly what it is. So we will construct a map from the curve to some changed curve, and then from this changed curve to a twice changed curve. And this homomorphism should be such that this here, that this is basically the same, basically again E, and that the composition of those two is multiplication by 2. And the procedure to go from here to here should be the same as the procedure of going from here to here. So I will just write down how this homomorphism looks like, and then we will look at some properties. So we have our elliptic curve to begin with. And then we say we construct this curve with a bar over it as minus 2ax squared and yeah, maybe this is a nice exercise to compute what happens if you go from here to here again with this one. But what results is this. And yeah. Yeah, thank you. Yeah, and yeah, good thing that you remarked this, because what we do here, if we have an elliptic curve, let's say like this, is that we want to change the variables such that we have at least one rational 2 torsion point, and this should be here. So we transform it. I don't know how it looks then, maybe like this. But we want one rational 2 torsion point in the origin. This is why we don't have the short Weierstrass form here, but we have an x everywhere. So 0, 0 is a point on the curve, and because it has x coordinate 0, it is also a 2 torsion point. Okay, and our homomorphism is phi from E to E bar, takes x and y to write that here. And since we divide by x here, we also define this. And we also want to define phi from E bar to E bar bar in the same way. Maybe it's nice to calculate if it actually gives this curve when you do this and how this looks here, but probably it's not nice to compute this Okay, and what we will use as black box because it's really technical, and I think even in the book they didn't do everything. They are homomorphisms. And the kernels are exactly the point at infinity and this 0, 0 point. Oh, and the composition is multiplication by 2. Okay. So this, we just take this for granted. We don't want to prove it. And we also don't want to understand how one could guess those homomorphisms, because this would also need probably some deeper algebraic geometry. I don't know what they say in the book. I think they say the same. I think they say something like, we magically put those homomorphisms out of our heads because it's so hard to explain how to guess them. And since they are so easily described, it's totally okay, I think. So maybe you will hear about this next week. Yes, next week I will not be here because there are some Berufungsvorträge to which you all are invited, I think. And there are some really nice applicants for the W3 position of I don't know whom, not Preda. And they will be on Tuesday, Wednesday, and Thursday, one in the morning, one in the afternoon. And since this is recorded, I will not tell you who's my favorite. I will say that maybe after I stop the recording. Okay, so we take this as a black box. Those are normal things that we would expect, and we also have some more properties. Of phi. Well, I take this all with a bar just as the point of an infinity of the curve E bar. But this is clear since we just define it like this. Then a perfect square is just a square in the rationals, yeah?
Why is pi of the point 0, 0 defined because we're dividing by x squared?
Oh yes, this is just the definition.
Okay, so the formula xy is left with this love plus 0.
Yeah, so this is, the definition is this if it's not 0 or this. And this otherwise. But thank you. Yeah, this I should be exact. So perfect square is just a square in the rationals. So a point on the curve E bar with x-coordinate non-zero is in the image if and only if its x-coordinate is a perfect square. So now it gets interesting, and now we get to algebraic number theory, because perfect squares are a nice thing to look at. And I think in 2 weeks, where we are going to talk about ranks, we will also do a lot with perfect squares. So first thing to notice is the image of phi has something to do with perfect squares. Second thing to notice, psi and phi, the composition of those is the multiplication by 2, and here we want to divide out basically the image of this. So we will be able to say something about the size of this using the image and using something with rational squares. So now we consider, and this, we will also not prove this. Maybe we will do something as exercises, I don't know yet. Black box. So now consider this map, sending the point at infinity to 1, sending 0, 0 to b from the curve, and sending a point xy to x. For x non-zero. Okay, so with this map and these properties, we have that the kernel of alpha is exactly the x that are perfect squares here, which is, bless you, exactly the image of this. And alpha is a homomorphism. Well, this is probably also very exhausting to compute. And since the kernel of alpha is the image of psi, we have that this is injective. And if we know now what the image of alpha is, then we can even say more about this. And how do we know what the image of alpha is? We want to know what the x-coordinate of a point can be modulo squares. So we're not interested in if we can divide out some squares or multiply with some squares. We want to know what we keep after dividing out squares. And we had a lemma or a step in a lemma in a proof where we found out that we can write the x-coordinate and the y-coordinate of a point like this. And now we can just plug this into our equation of the curve. And we get well, after we multiply with e to the 6, probably. Okay, we get this. And this is a square. So this here is also a square. But of course we don't know how are the prime factors. Is this a square and this? Or are some prime factors appearing here and here with multiplicity 1? So we have to find out how does the prime factorization of this look? Yeah?
How is alpha defined for a prime that is 0, y, which is not 0?
We let me think. Yeah, thank you. Okay, so we define now the greatest common divisor of those two. Because in the video no one can hear what was asked, I should repeat it. The question was what happens if x is 0 and y is not 0? And the answer is that this cannot happen. Okay, we have the GCD of this. So if D is the GCD of M and this, then it has to divide M. And since it divides this and it divides M, it also has to divide B to the BE to the 4. And here we also had this. So since the GCD, since M and E are co-prime and D divides M, then D has to divide B. And now return to this and see what we can say now about this. We can just divide here by D. And now we consider all the primes that divide M and not B. So, because primes that divide M and B, they appear with even multiplicity. Because in here we have them once, and at least once. So they have to appear here with even multiplicity, and here also. But the question is, what happens if a prime divides M and not B? With what multiplicity will it appear? I think I need a new board. Okay, so bin ich natürlich wieder reingetreten. So if we consider the prime factorization of n, then we have the primes that divide M and B, and we have the primes that divide M but not B. We don't have primes that divide any, because then they cannot appear here. Oops. And then we have plus or minus 1. Oops. Okay, now yes, now what I already said is that if they divide M and B, they have to appear with even multiplicity. So I can put a 2 here. And if they divide M but not B, then they have to appear with they can appear with even or odd multiplicity. So now we want to write m plus or minus a square times some prime divisors where PR are the prime divisors of B, and hence they can also, of course, appear with multiplicity 0 because they don't have to be the same. So EI is either 0 or 1. So what we have now is now we can look at what is alpha of P. If P is xy, so this is x modulo squares, but x was m over e squared. E squared, it's not, we're not interested in e squared, we're not interested in squares. So this is plus minus with the notation from before. What does it mean now? It means that, so B is just was just the coefficient from our curve. M and E depend on the curve. T depends on the curve. What Pi and epsilon I are doesn't matter for us. The only thing that matters is how many different possibilities do we have. We only have finitely many because those Pi are the prime divisors of B. They're only finitely many. So T is the number of prime divisors of B. And what we want to remark here is that the image of alpha, well, except for O and 0, 0, there are only 2 to the t times 2 possibilities. So 2 for the plus minus, 2 to the t for this, well, and plus those 2. So the size of the image is at most 2 to the t plus 1 plus 2. I think in the book they forgot this plus 2. But it doesn't matter because it's only about being finite. So why is this important now? Because we already showed that this is injective. So if instead of this here we put the image, we put the image of alpha, which is from this remark also the image of phi or psi, then we have a isomorphism. So what we have is that this is at most this, which is at most 2 to the t plus 1 plus 2. well, this is actually exactly, because it's also injective. And we said the composition of those two maps is the multiplication by 2. Oh, I just see that this, I wanted to put this as an exercise. Oh, well, but now I did it here. So this is at most 2 to the 2 plus 1 over 2, which is finite. And this is what we wanted to show. And so what we left out now was the technical details of those properties, the technical details that phi and psi are homomorphisms, and that the composition is multiplication by 2, and things like this. But we will use this phi later to say something about the rank of an elliptic curve, because what we now showed is that E of Q with the Mordell theorem is finitely generated. And a theorem that you probably had in some earlier lectures is that finitely generated abelian groups have a torsion part and a free part. And the free part looks like z to the r. We already know what the torsion looks like because we have Mazur's theorem, which tells us that there are only some, a handful groups that can appear here. But this is a total mystery. And it is actually also in reality a total mystery, except for sometimes we can say something. And you can do a lot of research on this R, and there are nice properties. So for example, I think if you look at all elliptic curves, then the expected value of R is like 1/2. And the maximum of a rank where someone could write down an elliptic curve, I think it's like 27. It's probably by Elkies. And this is crazy, that there isn't a known elliptic curve with larger rank. But yeah, it's a research problem. How large can the rank be? How can there be an algorithm that always gives us the rank? Because there is no such thing. There are only several ways of computing the rank that do not always work. Yeah, and we will talk about this in 2 weeks, yeah?
When we count the number of elements taken into account, should it just be 2 to the 2 plus 1? Because if we take all the exponents to be 0 or 1, we already get 1 and me. So like in the
Because you say that this is already included in here. Yeah, this could be, but I think...
like in the expression that was above.
Oh, yes, of course, yeah. Yeah, of course. If we have always 1 here, then we have B, and if we always have 0 here, then we have 1. Yeah, right. Thank you. But of course, this is still true. I can also put 100 here. But thank you very much for thinking. Yeah. Okay, then maybe see you next week at those Berufungsvorträge. If not, have fun with Julian next week.